So welcome back, everybody. I hope you can all hear me well, and I hope you're doing well, which is the most important thing. So just to quickly remind you of where we were on Monday. So on Monday, we looked at one of these examples, not too exciting, of an object which was falling in 2 dimensions and in 1 dimension. And this object was under the influence of the gravitational force. That is the analyzing part of the problem. And then there was also a force which was supposed to model the air resistance. And the thing we did on Monday was to take a force which depended only on the velocity. In that case, we had an object which we modeled in 2 dimensions. And we could actually integrate analytically the equations of motions, and we could find the velocity and the position as a function of time. This is essentially what we end up doing again and again in this course. So today, we are going to look at some other examples, a very, very famous one, the gravitational force. And then we're going to look at the spring force, which is another example we are going to actually derive when we come to harmonic oscillations. And then we're going to take a small look into homework set 2, which is due for Friday, which we also spend some time on Friday. And for those of you who are done with that one, you can start looking at homework number 3. And the thing with homework number 2 is that you have compact ways by which you can express an object in 2 and 3 dimensions. Or alternatively, you can spell out the X and Y coordinates as a specific array. And we're going to look at these kind of 2 different ways of doing it. So there is a kind of straightforward way where you just write all the variables. But in Python, you can also declare a vector as a function of time, which has X, Y, and Z components. And that gives you a much more compact formulation. But in the beginning, it can confuse people a little bit. So the example which we looked at on Monday is the case of an object falling in 2 dimensions. And we could integrate that exactly because the X and the Y direction didn't talk to each other. The problem which you have on the next homework set is a case where the drag force or the air resistance goes like velocity squared. And when we look at the problem in 2 dimensions, we can no longer integrate analytically. But this is something we will pick up again. Now, the example I wanted to bring up now is the gravitational force. And this is about apples. Why apples? So apples play, so you may ask, what is this guy talking about now? Is he going off on a tangent? He just brings up apples. Maybe because I have all these Apple gadgets. The thing is, according to legend, Newton was actually looking at falling apples on a farm in Lincolnshire outside London. Do you guys know why? He was contemplating, this is according to legend, but this is when he got the inspiration. He was only 23, and this was the year 1665. And then he got the inspiration for the model of the gravitational force. Do you guys know why he was confined to a farm in Lincolnshire? Anyone thought of that? Yeah. Yeah. So he been confined for 2 years. Newton was confined for 1 year in Lincolnshire because there was a plague in London. So the people who could afford it, they left the cities and went to the countryside. And that's when he came across this idea of the gravitational force. So this kind of pandemic may have some kind of positive consequences, but actually many people died. So I don't know whether the people who passed away thought that the discovery of the gravitational law was such a big thing. But there's something, actually, there's something very interesting as well. Since we are staying with legends and apples, so apples play a big role in history. We have the biblical apple, we have Wilhelm Tell in Switzerland, where he had to prove that he was such a good archer. So they put an apple on the top of the head of the sun, and he had to hit the apple. So, but Newton, when he discovered the relation between two objects which were rotating or orbiting around each other, it took him something like 20 years before this was published. Do you know why? Have you given a thought to that? It's actually an interesting thing. So from the, how to say, the discovery of this relation, or we got the idea for the relation, it took something like 20 years, according to legend, before it was actually presented in Principia. They needed differential calculus. So what Newton actually did in these years with collaborators was to discretize the equations and develop differential calculus like we are doing it when we do it numerically. Then later, when you took the limit when delta t goes to 0, you could then say that, okay, this defines a derivative. But what they actually did was to deal with finite discrete elements. And then they developed differential calculus, which we, in a way, actually using when we are solving the equations numerically. We are discretizing. So I started with apples, and we ended up with the differential equations and the discretized equations. So there are many interesting links. So from when you discover something till you actually present it, or you present it in what you think is a meaningful way, it can take quite some time. And science is, and physics is full of this kind of things. Like when Einstein wrote this paper about the photoelectric effect, it wasn't before the 50s and 60s, roughly 50 years later, when people actually came up with the laser and the photocells, which you see in every building. When you open a door, you just cut off the light beam and then the door opens. So there are many things which sometimes take a lot of time before you actually see them presented, or even in terms of something which can be used. So let's go back to the, this was a digression, guys. I hope you can excuse me, but I thought this link with apples was pretty neat. And Michigan is actually, by the way, the state in the US, which is the third largest producer of apples. All right. Okay. And I promise to be a little bit more serious now, okay? So let's look at the, switch to the whiteboard here and look at the equations which Newton actually put forward and the way we are going to analyze them a little bit later. So we looked at the case of an object which was falling, but now let's look at the next example, which is a gravitational force. So this is our second example. And in this case, what we would have is a gravitational force. And now we are looking at the example of the Earth-Sun case. And when we look at the force from the Earth to the Sun, this is something which contains the gravitational constant, the mass of the Sun, and I guess many of you have seen this symbol before. So this circle with a dot inside is the mass of the Sun. And then it's multiplied with a vector r, and it's divided by r cubed. So this is the absolute value of the distance. Now this, I guess, how many of you are actually doing astrophysics and astronomy? So that means that you know the value of this quantity, right? So if we take this, the distance between the Earth and the Sun, does anyone remember the numerical value of it? Okay, it has a unit. There is a specific unit which is being used, right? The astronomical unit, right? So this is normally written as 1 AU, astronomical unit, and it has a value which is 1.5 times 10 to the 11th meters. So anyone who remembers the mass of the weight of the Sun, roughly? Order magnitude? Yeah. Yeah, roughly, yeah, that's exact. So this is typically 2 times 10 to the 30th kilogram. Anyone who remembers the mass of the Earth? Roughly. Orders of magnitude. Yeah, exactly. Yeah. So I don't remember the exact digits, but this is 10 to the 24th kilograms. So it's 6 orders of magnitude less than the sun. So if you guys get stranded on a remote island, the only thing you need to bring with you is a table of physical constants, and then you can do everything with that. Okay. I promise the second time to be a little bit more serious today. That's okay. So if we look at the problem in 2 dimensions here, and this is a very good approximation. So when we are going to solve this later in the semester, yeah? Okay. Yeah. This was stuff that wasn't it? Okay. Sound problem in the audience here. So hopefully the people in the audience will hear better now. There's always a kind of delicate thing when we have this hybrid mode. Okay, so when we move to 2 dimensions, the problem which we then have is a problem which is a pretty good representation of what is going on. And we would then have the radius or the distance from the Earth to the Sun, which is given by x squared plus y squared. And now we are thinking of the Earth as the object which is rotating around the Sun, and the Sun is the origin of the system. So you're making a coordinate system where the Sun is at the center. And this is a very good approximation because the Sun is 6 orders of magnitude more massive than the Earth. So when you see things like that, it's a very good approximation to assume that one of the objects can be put at rest. Then we know that the x then is given by r if we now make a small figure in 2 dimensions. So with x and y, so we would have the Earth here. And then we have the Sun here. And this defines the distance from the Earth to the, yeah?
Professor, you're not sharing
Yeah, I'm getting confused here, guys. So I started telling too many jokes today, and then I just got distracted. Okay. Okay. So for you guys online, we had a small mess with the audio, and then I forgot to put back the whiteboard here. So what we are doing now is that we are setting up a system in 2 dimensions for the Earth-Sun system, and this is a pretty good approximation because the Earth exhibits elliptical orbits around the Sun, and approximating the system to a 2-dimensional one is a pretty good approximation. So this kind of exercise, which you see here, is something which we will pick up a little bit later. And one of the typical problems you're going to solve numerically is actually this type of problem. And that's a kind of warm-up exercise before we start adding more planets. So the x value is then obviously when we look at the angle here, we define an angle theta, That means that x has to be equal to r times cosine theta. And this is obviously the absolute value when I don't put an arrow on top of it. So I would typically write it like this. And y is then equal to r times sine theta. That means that there is a force in the x direction, f of x. And now since this is, we are looking at the force which the Earth feels from the sun, then it has the opposite sign. So this is Newton's third law. So that means that there is going to be a minus of g times the mass of the sun, the mass of the Earth, divided by r cubed. And this is now multiplied by x. So what I did now was to get the x component of the force. And similarly, if I take the y component, this is simply given by minus g times the mass of the sun and the mass of the Earth multiplied by y and divided by r cubed. That means that the acceleration, and when we are setting up the equations of motion here, it means that we have an acceleration in the x direction, which is given by minus g times m, the mass of the sun, multiplied by x, divided by the distance cubed. And this distance now depends on both x and y. So that's the reason why we cannot solve analytically this system in the Cartesian coordinate system, because we cannot separate x and y. This is more or less the same as the problem you're going to see in homework number 3, where we have the velocity squared in 2 dimensions, and then we cannot set up a expression which we can solve analytically if we insist on Cartesian coordinates. So after spring break, we are going to look at how to solve this system by making smart transformations to spherical or polar coordinates. Then we can actually find an analytical solution. But when we do it numerically, we often just stay with a Cartesian system, which is often the one which is simpler to implement. So that means that the acceleration we divide by the mass of the Earth. So this is the acceleration of Earth in the x direction, and this is the acceleration in the y direction. And then we would have mass of the sun times x divided by the distance cubed. And we know that this is again equal to the derivative of dvx, no, sorry, dvy. So the velocity in the y direction and dt. And this is again equal to dvx of dt. And finally, we also have that vx is the derivative of x with respect to time. And we have that v of y is equal to dy dt. So these are the equations of motion which we need to solve if we take the Earth-Sun case and we look at the gravitational law. And this is a fundamental law in nature. And we want to solve it in 2 dimensions. If you now add the 3rd dimension, it's pretty easy to see that you get 6 coupled first-order differential equations. And these equations which we then cannot solve analytically when we move on to more and more objects. So the second midterm is about you writing a code to simulate the solar system. So that means that you're going to have repeated types of equations which look like this, but which then will represent the interaction between the Earth and the Sun, the Earth and Jupiter, and all the other planets. And then we have a way to model the solar system. And these are the forces which we think are the important forces for a gravitational problem. Another type of problem, which we are going to spend a lot of time on. So this is example 3 here. And example 3 is that of a block which is sliding on a plane. And if we look at that in 1 dimension, so we would have the x direction here, and we have this block which is sliding back and forth. And this block is fastened with a spring. And what we know then is that there is a force which acts on this block from the spring and vice versa. And if we don't have friction, this force is equal to a constant, which we normally call the spring constant, multiplied with the displacement. So this is an experimental observation. And there is a famous law, which is called Hooke's law, which says something about the range of validity of this approximation. So when we come to harmonic oscillations, a little bit later in the semester now, we're actually going to derive this force as a Taylor expansion. And we're just going to keep the first terms in a Taylor expansion about the potentials around a 0 point. And then we're going to see that the first terms in the expansion correspond to this force, which is proportional with the displacement. So the typical thing here now, we can choose a displacement which starts at a given 0th point. So we could have something which goes like this, but it's pretty normal to choose the origin so that an x0 is equal to 0. So you could now think of this as being the x0 as being at the position where this object is at rest. But then it's common, since you are the one who can choose the origin, you would typically set this x0 to 0, because that often simplifies life. So it means that the force which you have, and now we're still in 1 dimension, you can easily extend this to 2 and more dimensions. And note that when we are not dealing with things in more than 1 dimension, we take away the arrows for vectors. So we put x0 to 0, and that means that f is equal to minus k times x. So it's proportional with the displacement. This is an empirical observation. So there is no fundamental law which gives you this behavior. And this object is going to oscillate back and forth around an equilibrium position. And we are going to study this system in quite some detail, because this system is important in the development of many mechanical devices. So if you're looking at your car, when you're driving on a rough road, there is always some damping, and this damping is very much fine-tuned to the car itself. And what is being modeled then are equations like this with some additions, with damping terms, and there can be an external force which apply to it, and so forth. So this type of equations are equations which we are going to see again and again. And if we now bring in Newton's second law, we know that this is the acceleration, which is a second derivative position. So this is minus k times x. This k is normally called a spring constant. So there's a constant, a material specific constant. We would typically divide by the mass. So we would define a parameter which is called omega 0, which is k divided by m. And this is called a natural frequency. And you will see that when you look at the dimensions of it, this quantity omega 0 has dimension 1 over time, inverse time. So this means that we can rewrite the equation of d of second derivative with respect to time, which is now the acceleration, which is given by this minus omega 0 squared times x. This is also an equation which has analytical answers. And in this specific case, and we will show that later, the answer is given by some x of t. And you can see that by plugging it into the differential equation. It's going to be given by a cosine with an argument omega 0 times time, plus a constant b times a sine of omega 0 times t. So these are examples which we are going to look at in more detail in some few weeks. So I guess we're going to look at this in 3-4 weeks now. And then we're going to spend a lot of attention on a system in a harmonic oscillator. These are typically called harmonic oscillators. And we are going then to look at the damping of the motion. We are going to look at an external force which is being applied to it. In some cases, we can solve it analytically, but in most cases, we will solve it numerically. So these are very common systems in mechanics, and the gravitational force and the sort of harmonic oscillations are things which we will study in much more detail. But now I simply wanted to mention them because you see now the differential equations which come up here. So you have the equation of motions, which are given by the force. So that means that when you are writing a program now, in this specific case, if you look at this problem, the only thing you need to plug in is the expression for the acceleration here. And this is the equation you would have to set in. So one thing I wanted to do now, unless you have some questions, things which are unclear, is to go a little bit back to what we discussed on Monday, when we set up the program for studying a falling object. But this program is very generic, because as soon as you have analyzed the problem and you found the forces which are at play, then the only thing you need to set in the code is actually the acceleration. So let's take a look at the code which we had last time. And let's share screen again. So one of the things which we looked at last time was the code for a falling object. So let's bring this back again. And the equations which we solved then was an equation which now involved the acceleration. And this is a one-dimensional problem. So it's an object which was falling in a gravitational field, where you have the gravitational acceleration, and you had a drag force which is proportional to the velocity square. Now, in this specific case, we could integrate up analytically. If you now look at the code which we got after we discretized the equations, and this is actually what Newton, according to legend, spent something like 20 years to develop before they could actually present the gravitational force and these laws of nature. But what we did then was to set up a code here where we looked at the basic equations we want to integrate up. So we are defining time, that's an array with the n elements. We have the acceleration, the velocity, and the position. And in this specific case, we are just dealing with one-dimensional arrays as a function of time. So time is a variable which changes. And there is no need to define a vector for position and velocity because we are just in one dimension. And this is the kind of notation which we normally would use when we are just in a one-dimensional case. So that means that we would have to specify some initial conditions. In this case, we also have analytical solutions. And you see now that what we are doing here as a function of time is to set in the expression for the acceleration. So if this had been the gravitational force, you would have to change this expression. And then you see now we are using Newton's Euler's method to simply integrate up the position and the velocity. And then we need the expression for the acceleration. This is in case we just deal with a problem in one dimension. Now, one thing you could do then, when you move to 2 dimensions, and now we need to look at the problem which we had on Monday. So if we look at the code then, and what you could do then is simply to define the velocity in the y direction, the velocity in the x direction, the position in the x direction, and the position in the y direction. So this is, there is no problem in setting up an array, a one-dimensional array in time for all the quantities you want to calculate. So remember again now that what we did on Monday was to look at the system in 2 dimensions. And then we had equations of motions for x and y. So in this specific case, what you need to do then is simply to, and here I'm not giving you the full answer because you're actually supposed to do that in homework number 3, but you have the basic body here. And then what you need to do then is simply to plug in the velocity in the x direction and the y direction, position in x and y here. And then you do the specific upgrades, and you also need to have the acceleration in the x direction and the acceleration in the y direction. Now, Python allows you to write this in a much more compact way. And the way you could do it is as follows. So let me just write it down on the whiteboard here, because this is a kind of subtlety which sometimes confuses people in the beginning when you start using Python. So if you look at a two-dimensional vector, you could actually define that in a much more compact way. So if we now move down here a little bit, and we want to define a two-dimensional vector, so we have a compact notation. And in the beginning, if you're a little bit unsure, I normally recommend to use this kind of straightforward notation where you write explicitly out the X and the Y components. And if you're dealing with a three-dimensional one, you can write out the Z component. But if you do this in a more compact way, what you would define then, you could now define, since you want to have time, so let's say we stay in 2 dimensions. In this specific case here, we would define, let's say, position like this. So we could have a vector R. And now we want to put it to 0. So we would have a numpy function, which we use here. And then we would have something like n time steps. So these are the n time variables. But now what we can do is actually to add the dimension of the system. So what you would have here now is the dimension. So this could be now a 2-dimensional object. So it means that the first component could be the X value. And one way you could do this now is as follows. So in reality, this becomes a matrix. It's a matrix, for those of you who are familiar with linear algebra, it's a matrix of dimensionality n times 2. But this is hidden for us because NumPy does this in a way behind the curtain. And it gives us a very compact notation. So you should feel free to use the way to program which you feel comfortable with. If you think it's more easy to write out every quantity like velocity in the X direction, velocity in the Y direction, so on, do that. So we are not degrading you on beautiful programming, but we're actually looking after your physics insights. So what you could do now, if you want to define the initial conditions, there's one way of doing that, initial condition, and you could define a quantity now, which you would call R0, like this. And this is something you would set up using the array functionality in NumPy. And you would write it like this. So this could be 0, 0, and this could be x0. And then you would have a new quantity, which you could also define to be 0, or whatever kind of number. This is up to you. And this would be y0. So it gives you a much more compact way of setting up a specific quantity. Then you could now initialize the vector, or actually the matrix R at t equal 0. And then you could simply write it out like R of 0, the first element in time, because then you suppress all the other notation, and you would simply write this as equal to R0. So it takes some time to get used to this kind of notation. You will see some of it in homework number 2, when you're looking at this object in 2 or 3 dimensions, where you can use that kind of notation if you want to. But if not, I mean, just stay with X, Y, Z. If you feel that this is a little bit too compact, okay? But these are things you should keep asking about, because the Python has an extreme flexibility, and sometimes you get lost because you don't see the wood for the trees. There are too many options, okay? So if we now take a look at the exercises, one of the exercises in this week, exercise 5 in homework assignment number 2 here. This is a case, I don't know how many of you had time to look at it, but I just wanted to give you some hints, because this is often when you go into my textbooks, you have to figure out what they're actually asking for. And it takes some time to decode the initial conditions and then set up the equations. So this is a example which is taken from the textbook of Taylor, and it's exercise, I think it's exercise 138. So this is Taylor 138. And we're also going to discuss these exercises on Friday. In this specific case, we have an object, a puck in this case, which is sliding on a board. And we're assuming that it's not leaving the board. So this board has a certain inclination. And then the forces which are at play is a normal force from the board to the puck. And then there is a gravitational force. These are the only forces which are acting on the system. So let's just write out these things which are relevant for the homework. The exercise before that is pretty similar. That's a golf ball. And that's the one you're going to compare with your numerical program. So you're going to plot the same things, and you can then use the compact representation of a vector, or you can just write out the x, y, z components. But this specific exercise, so what you can do now is that you have two forces, and it takes some time often to decode the exercise. So you have a normal force, where we can assume now that it has a magnitude n. So let's just write that with a magnitude n. And we assume now that, as it says in the exercise text, and perpendicular to the board. So we're also assuming that this object is not leaving this board. And we also have gravity with magnitude mg. I just write mg here. And this is pointing vertically downwards, right? So the way we can split the problem here is in the following way. So we can have the two components, because this board is a little bit tilted. So that means that when you take the gravitational force which goes down, you could now think of there's a component which is perpendicular to the board, and there's a component which is parallel with it. And then we can split the motion of this puck on this board. So we are going now to look at a problem here where we fix the x-axis. So we have no force in the x-axis. So this is given by m of d derivative dx of dt. And we would typically write this in a more compact notation like x with these two dots on top of it. That's a kind of compact notation for the second derivative with respect to time. Then, if we look at the y direction, then we are assuming now that in the y direction, there is a force which is perpendicular to the board. So this board is a little bit tilted. So that means that what we would have then is something like a minus mg, and then we have an angle theta, sine theta. And this is equal to the derivative, the second derivative of y with respect to time. What we're also moving now, what we assume that this object here, the puck, doesn't leave the board. It remains on the board here. So that means that since it remains, what we would have then is a gravitational force which acts on it, and there is a normal force from the board, and they two cancel each other because the object doesn't leave it. So this has a consequence. This means that the net force in the x direction no, in the z direction, sorry, is equal to n minus mg, and multiply with cosine theta. And this is equal to the acceleration in the z direction. And we put that one to 0. So there's 0 force in this dimension here. So there is a normal force on the object. And then there's a component of the gravitational force which acts on this object. And they equalize each other because it doesn't leave it. So if it had left it, it would have been much more complicated. So sometimes it takes, I'm doing this now because I hope you don't get offended if I give you partly the answer here, but it's more because sometimes many of the exercises can be a little bit difficult to decode. What are they actually looking after? And I have to confess, I had to look up the answer because I didn't understand the text the first time when I read it. Okay. So if you have problems in decoding the text, you're not the only one. Okay, so that and what we have in addition are some initial conditions, which we always have to specify. So if we set up the initial conditions, what we get then is an R0, and we fix that one to be 0, 0. So we have no position, so we just place ourselves in the origin for this system. And then we give the system also an initial velocity. So there is an initial velocity in our chosen x direction. There is an initial velocity in the chosen y direction, and 0 in the z direction. So without doing any calculations, if you now look at the differential equations we have, so let's bring that up. We have one for the z direction, we have one for the y direction, and then we have one for the x direction. So we have an initial velocity in the x direction. And if you now think of integrating up the equations, if you look at the equations in the x directions, what kind of velocity would you get when you integrate up? So let me just put down the equations now. So what we have is now the acceleration in the x direction, which is given by dvx of dt. And what we did now was to assume that the force in the x direction is equal to 0. So there is no acceleration. Do you need to do any calculations for this case? So what would the answer be? Yeah, it's just a constant velocity, right? So you start with an initial velocity. So when I integrate up here, if I integrate up the velocity, or start with time t equal to 0. So if we say t0 is equal to 0, and we integrate up with the acceleration here from 0 up to time t, and then we take the dvx dt, we are simply going to get this one equal to v0 times x. And this is going to be the velocity. So I'm just writing it like this. So this is the velocity in the x direction. And if I integrate up again, and I find my x value, so we're going to see that the x value, since the velocity is constant, this is simply going to be the initial velocity time. So in this case, we don't need to do any calculation. We can just read off. There is no acceleration, right? So the velocity has to be constant. And if we give it an initial velocity, that is the velocity. And that means also that the displacement is simply that velocity times time. So in this particular case, there's no need in doing any calculations. Then you can do the same thing for the velocity in the y direction. So what you would need then, so in the y direction, what you would find then when you integrate up is simply that you would get a v0y minus a g times sine theta. I'm just giving the answer because integrations are pretty easy. So this will be vy of t. So if you look at the z direction, and let's put up the velocity here. So if you now go back, so let me ask you, what would you expect when you have this force in the z direction? So what does your intuition say? So this is a case where also the acceleration is equal to 0. So that means the object, and we started with an initial condition where we put the initial velocity to 0. So it should remain at rest in the z direction. So that means that then that the velocity here, v of z, the function of time, is simply equal to 0. And that means that we can then integrate up, and since the velocity is 0, it doesn't move, right? So we get then a position here, r of t, which is now equal to v0 x, constant velocity. There is a new one here when we integrate up with respect to y. So we get a multiply with t, and then we have a minus a half g times sine of theta, and this is multiplied with t squared, and then we have 0 position in the z direction. So this will be part of the answer, and then you're being asked what happens when it reaches the floor. What would the final time be? And with the final time, you can also find the position in the x and the y directions. But that's something which we're going to leave to you guys to look at. So when you're going to code this, you can obviously set up everything in terms of x, y, z, vx, vy, and vz. But alternatively, what you could do is to use this more compact notation. And homework number 2 in the numerical exercise, there are many small hints and guidelines on how to do that. So feel free to do it like that. Or if you feel not too familiar with this kind of Python compact option using numerical Python, which actually allows you to do complicated operations on arrays without actually having to write a code for it, just feel free to use the way you think you are most familiar with. But what you need to do in the numerical exercise is to plot the positions in the x, y, and z directions. And you're going to compare that to the analytical calculations from exercise number 4, which is about a golf ball. But essentially, the kind of things which you see here in this exercise 5 and exercise 4, they are pretty similar problems. This is an object which is either sliding on a board, or it's a golf ball, it could be a falling object. So these kind of problems which we have seen till now are the kind of problems which we are going to call the warm-up problems. And on Friday, the thing we are going to discuss first, we are going to look at partly at some of the other exercises, but we will also start with something which is called the work energy theorem. And that's what's going to bring us into some new stuff, because then this is going to lead to the many important aspects in mechanics, which deal with conservation of energy, conservation of angular momentum, conservation of momentum itself. And these are quantities which play a very, very important role when we analyze a physical system. So on Friday, we're going to start looking at the work energy theorem, which then is going to have important implications for the type of forces which we are looking at. And next week, we are going to look at things which perhaps you have seen before, but we are going to formalize them. And that deals with conservation theorems, which play a very important role in mechanics. So I'm going to stop the recording here now. And it's 10 to the hour soon. And on Friday, we spend this 15, 20 minutes on a little bit theory and some of the exercises. And then the rest of the time is dedicated to exercise solutions. And I apologize for the microphone problems we had in the beginning. Okay, guys. And we have office hours. So if you want to hang around and ask questions, I'm here till 5 o'clock roughly. And for those of you online, feel free to hang on if you have questions online. Julie and George are also online, so they will also participate in the chat and the discussions. Okay, have a nice day, rest of the day, all of you.
Can I share my